This is part 2 of the transition metals lesson. Okay, well, how could we find out if a metal was more reactive? Now, you've probably done this experiment in class before, especially if you're in my class, because you know how I like to blow things up. You've got here 5 test tubes with hydrochloric acid in it, dilute hydrochloric acid, and you've got different types of metal in each of them. Now you'll notice you've got the same amount of acid and you've got the same amount of metal, so you've got a fair test. And what we're doing is we're testing to see for a squeaky pop. Now hopefully you know that the squeaky pop test is to test for the gas hydrogen. So how much hydrogen are we making? Now if you look at those diagrams, could you write an order of reactivity? If you want to pause and have a go, do so. If not, continue. So, well, you might look at the number of bubbles in the dilute hydrochloric acid, or you might look at the amount of gas being made. So we've got a very loud squeaky pop here with magnesium, and we've got a no chance matey with copper. This is straight out of the revision guide, guys, so if you want to see it again, it's there. So what about it? Could I put them in order of reactivity? Well, hopefully if you've tried, and I do hope that you have, you'd have magnesium as the most reactive, then aluminium, then zinc, then iron, and copper being the least reactive. It doesn't even look like it's doing anything. Would these metals react with water? Well, probably not very quickly, definitely not in the lab, but you do need to be aware that some of them you can react with steam. Now obviously steam is still water, it's just got more energy. So some of the more reactive ones, maybe the magnesium, the aluminium, you could use this apparatus you can see here and heat up the water in the mineral wool until you get hot water, steam, and that may just react with maybe magnesium, maybe aluminium, maybe even zinc to get enough hydrogen to get a reaction, to see you've got a reaction. Okay, so if we look at these 5 here, you'll notice magnesium is the most reactive, is over here in group 2, and then we come across here to group 3, and then we come back again to the transition metals, and there's an order there. Group 2 is more reactive than group 3. And then the transition metals are even less reactive. Now there's a couple of others here that you might recognise that we normally include in a reactivity series. We've got calcium here. We often include calcium. I've also included this one because I know you lot always forget that calcium is a metal. Yes, the stuff you drink in your milk. Yes, it's a metal. Yes, it's good for your teeth. Okay, you've just got to get your heads around that. I know it's weird. We've also talked about some of these here. So silver, and we've just talked about gold, and the other one that you might often see included here is the platinum, but you'll notice they're lower down in the transition metals. Now, is that it? Is that all the metals we know about? Is there possibly another group that we've discussed in great detail that we could add to this list? I'm hoping you've said yes, and I'm hoping that you've remembered we've done the alkali metals, haven't we? So where do you think they'd be? So we had group 2 was more reactive than group 3, and then the transition metals were later. So where do you think group 1 would be? Could you predict that? Well, I'm hoping you predict that they'd be even more reactive than group 2. We're getting more reactive as we come back down these groups. Well, I am not going to bore you to death with the alkali metals. We've done this experiment, haven't we? We tested them in water. You can imagine now why we don't test them in acid, far too dangerous. We tested them in water and we discovered that as we went down the group, they became more reactive. The reactivity series tends to only look at these first 3 because they're the only ones we tend to use in the lab. The others are too dangerous. So if we look at this here, after calcium, so I'm looking for my least reactive for there, so lithium and then sodium, and then potassium being my most reactive at the top. Hopefully you can see where I've got the information to build this reactivity series. So the big question then is, why are some metals more reactive than others? We've already established that the metals lose electrons, and we know as we go down any group, whether it's group 1, 2, 3 or the transition metals, the atoms are getting bigger. and therefore they become more reactive because it's easier to lose that electron. We've done that a couple of times now already. So it makes sense as you come down group 1, they get more reactive. As you come down group 2, they get more reactive. As you come down group 3, they get more reactive. And even the transition metals, as you tend to come down, they tend to get more reactive. They're a little bit more complicated, which is why we don't do them in a lot of detail. But why is group 1 more reactive than group 2? Well, group 1 has only got 1 electron in its outer energy level. It only needs to lose 1 electron. Group 2 has got 2 electrons in its outer energy level, so it needs to lose 2 electrons to become stable. Group 3 has got 3 electrons in its outer energy level, so it needs to lose 3 electrons before it's stable. Now again, the transition metals are a little bit more complex. They do form the positive ions, but we're not going to worry about how many. If we look at these atoms, however, group 1, group 2 and group 3, you'll notice they're all the same size. So these are going to be at the top of each group. So they're all the same size. They've all got the same amount of electrostatic attraction. What's the difference? Well, the difference is the number of electrons they've got to lose. Group 1 only has to lose 1 electron and it's happy, it's stable. Whereas group 3 has got to lose and give away 3 electrons before it's stable. So as we go across the periodic table, group 1, group 2, group 3, and then the transition metals in the middle there, it gets harder to lose all the electrons that it needs to in order to become stable, and therefore it becomes less reactive. So as a general rule for any metal, whether it's because it's bigger, so it's easier to lose, or whether it's because it's got less to lose, the general rule is the easier it is for the metal to lose the electrons and to become a positive ion, the more reactive it is.